Okay, in my final video from post 2002 libmapper workshop, I'll be presenting a proposal related to self-timed maps. So, as you probably know, currently maps in libmapper are always updated asynchronously. That is, they only are processed when the input changes, or one of the inputs changes for a convergent map. And various projects that we've done over the years, including MapLooper, have worked around this by either using an intermediate device or just making sure that the source is updated periodically. That said, there are some obvious potential benefits to having synchronous, like periodic processing of maps. First one is more consistent filter behavior. We support in our expression engine unit delays for FIR and IIR filters, but their frequency domain response is very unpredictable, obviously, if the input or if they're not being calculated at a periodic rate, if the samples aren't evenly spaced. Also, we could imagine things like modulators, like LFOs, as part of our maps, up and down sampling, triggered envelopes and ramping. So we could use inputs that are event-based, like MIDI, but then map it to envelope processes. Also, of course, sequencing and live looping, building on projects like MapLooper. And finally, synchronization of remote peers, which we were working on actually back in 2013 in the metronome branch on GitHub. And that kind of it came before, but is similar to what Ableton released in 2016 with their Link project. And so we would be aiming for allowing the same kind of distributed synchronization, but I think we could do it in a way that's a little more flexible and perhaps interesting than Ableton Link. And we try to interface with Link that was part of this. So my proposal is that we actually extend the expression syntax to allow specification of separate blocks and three different types of blocks in particular, which I'm calling init, event, and periodic. When the expression was compiled, these blocks would be sections of the expression evaluation stack, just like functions are on a normal program stack, on an instruction stack. And we would store, as part of the map expressions, pointers to the beginnings of each of these sub sections of the stack. And I'll talk about them in detail. So first is the init block, which would run once when the expression is created. This is a little different from our current evaluation optimization that we do. You may or may not be aware that currently when a map expression is evaluated in libmapper, we actually advance the pointer to the start of the stack if it has not used any variables or any random functions or anything like that. So if it's just variable initialization, it won't be evaluated. That part of the stack won't be evaluated in subsequent calls. It's just for a bit of optimization. But we do reset that every time a new instance is created in order to make sure that instance variables are initialized properly. So in this case, this would be different. It would just run once when the expression is created. We use it to initialize global variables. By global, I mean non-instanced, so that are shared among all the signal instances. But it could also update the destination of the map to some default value. Next comes the event block, which would run whenever the specified signal changes, which is basically our current behavior. But I'm suggesting we have three different variants based on the signal event types that are part of the libmapper API already. So that's new, update, and release. And interestingly, we could define multiple event blocks, either for different signals, in the case of convergent maps, or for different events, or for both. And we maybe could have a discussion about how we could define a block that might be called for more than one signal or for more than one event, whether we use vector arguments or some other method to indicate that. So the new variant of the event block would run only when a new instance is activated, could be used to initialize instanced user variables, And we'd have to consider whether or not you could use this block to actually override the default libmapper behavior for a new instance. So for example, perhaps in this block, you could check to see whether the instances have been, whether you have an overflow, you've run out of instances for the destination, and you could reject the event or call some custom code that actually releases an existing instance. Event update would run whenever the signal value changes, and so basically this would function exactly like what we have now. And perhaps this is the default if you don't specify a variant, if you just call event, but we don't necessarily need a default. We'd have to see. And finally, release would run only when a signal instance is released or deactivated. And interestingly, perhaps that could be the destination signal. libmapper already supports propagation of release information from downstream to upstream, so that you could know if some device that you're controlling has released an instance. So maybe we should allow access to that in the expression itself. And similarly to new, this could override the default behavior for release event. And in the little example here, all we do is when the source of this map, x0, is released, or when one of its instances are released, the corresponding instance of the destination y is released, but first it's set to 0, rather than just being released immediately. And then we have this periodic block, which, unlike the others, would be scheduled by libmapper internally during device polling at some rate. And so this would be borrowing directly from the old metronome branch, which we haven't updated since 2013. And we could define multiple periodic blocks within a map expression that could be specified to run at different rates. So we could compare this to C-sound kind of control versus audio rate. We could use it for doing polyrhythms if we have them in geometric relationships. Or we could use it for phasing. If the specified periods are very close to each other but not quite the same, then we could have kind of Steve Reich-like patterns produced by our maps. A scalar argument to the periodic would specify the callback interval, so the period. I'm not sure it should be in milliseconds, since all our timestamp information in expressions so far is in seconds. So perhaps they should be in seconds rather than milliseconds, but that could be something for the group to discuss. As an interesting quirk, I'm suggesting that a vector period, rather than scheduling multiple different periods, would actually schedule a pattern. Because remember, we can use multiple periodic blocks if we want different periods. So we could use this for something like shuffle. If you were using this to build an arpeggiator, you could have shuffle built in. Or it could just be a pattern like this. So 211 times 500 milliseconds. And so basically in this pattern, we would be triggering an output. May also be worth discussing whether there should be any additional special variables accessible within this block. Perhaps T refers to clock time since quote unquote start, which I'll discuss in a moment. And then I have N referring to logical time. So the number of times that periodic has been called, or the number of times that the pattern has been repeated. And B would be the current pattern index. Now, N and B are trivial to compute within a user expression just by incrementing a counter. But in terms of supporting ease of use, perhaps we could consider having these special variables. Now, start is kind of an interesting concept when we're talking about distributed synchronization, because it's what really determines the phase of our periodic functions, right, of synchronization. And so we could talk about there being several useful baselines. NTP epoch is kind of an obvious one since we're using NTP time tags already, but it could be the creation of the map, it could be the creation of one of the signals involved in the map, or instance activation of one of the signals involved in the map. It could be a session start time, so this is the start of our start of our jam that we're doing together, start of a piece. And that then leads to perhaps it should be something like transport control, which is very much like a session start time, except it also has the state, whether it's running or not. So a transport can be paused, can be restarted, and it can be reset to zero at the current time. And actually, often they have an like I'm actually forgetting the term, but it's like anacrusis. Like you can do a pickup before the start time, or basically you schedule your transport to start 2 bars in the future at zero. So you actually started at negative, at a negative value. So in terms of distributed sync, basically we need our different peers to agree on a common baseline for start. And then based on the differences between their various clocks, we can actually have them synchronize with each other. In order to do this in a flexible way, I'm suggesting maybe we use signals to actually distribute the start time. So you would call a signal as an argument for the periodic block, and it would use the value of that signal for the start time. We'd have to figure out where that fits in terms of the arguments to periodic. Is it an optional second argument, perhaps? And then interesting question whether we should use instances for transport control, since instances also have this additional state that whether they're active or not, which could be analogous to whether a transport is running or not. So the value of the instance would be it could actually be the start time of the transport, and if it's active, then the transport's running, and if it's inactive, then the transport's not running. Now, in libmapper, instances are not just, they can be ephemeral, but they can also be multiplex. So perhaps this leads to thinking about multiplex transports, which we should probably discuss with the ASIA group, since I think this is something they have probably been thinking about in terms of their scripting control, though they don't really address instance control, but maybe they'd be interested in it. This sounds like a thesis topic to me. So I presented in the intro video that was posted earlier some simple examples of arpeggiators. So here's a revised example. It's actually the same simplicity, but now it runs at a periodic rate, not determined by the input. In fact, the input is not mentioned in this specific expression. So you see we've scheduled a pattern, or we've defined a pattern, which is just a vector. And we have a vector of pitches, and then periodic is called with this vector as an argument. And of course, this vector could be dynamically changed. Every time we run periodic, we would be looking up the next time that it should be called, that the callback should run. Yeah, and then inside the periodic function, we're just incrementing, we're just iterating through this pitches vector. Here's the example with input. So on either a new or release event of the source signal, we concatenate the values of all of its active instances and sort them, and that forms our vector of pitches. And then at a periodic rate, we play the arpeggio. Now we're getting more complex. Here's an exponential envelope follower. Should say as a caveat, none of these are working examples. This is just trying to define a good direction. So these are not functional yet. So an exponential envelope follower is actually pretty simple to implement. We just use the EMA function, the exponential moving average, to follow the input with a weight of 0.1. And then we're just using the new and release event blocks to manipulate a user variable called active. And basically the only reason we're doing that is because this expression will allow the envelope to decay to zero, well, technically to epsilon, but decay below epsilon before the destination is released. So even after the source is released, this envelope will continue running, decay, and once it's below epsilon, the alive variable will be set to false, and the destination would be released. Here's a simple linear envelope with attack and release variables. And so basically, whenever there's a new or an update event, we would recalculate this increment variable based on the distance, the difference between x and the last value of y, and the attack time and the period value. And then once we get a release, we recalculate so that we would decay to 0. And then the rest of it's very similar. The periodic similar to the exponential example. Sure, it would be nice if we could do an ADSR envelope, yes, which actually ends up being a little bit complex. So use new and release in the same way as before, but in order to track our progress through the ADSR envelope, that state ends up being quite complex. This is at least theoretically working example, but you see I had to use the Schmidt trigger twice in order to track the state. And I would say that this is not an expression that we would expect a reasonable user of libmapper to be able to write during some mapping session. So I think we need some expression language support to make this a little bit easier. In order to provide that support, I'd suggest something like an envelope function. And from my brainstorming and sketching, the simplest thing I could come up with is actually something that is a little bit different. It kind of stretches the way we've been using user variables, but it would actually basically it would create a data structure. So it's like it's a user variable that has structure to it because it has to store the start time, the durations, the destination values, etc. Say that the arguments could be scalars, vectors, variables, or expressions. And we'd have to support instanced and multiplexed variables. Perhaps a missing duration would just default to 0, so it would just jump to that value if there's no duration. And we need, or at least I think it would help for tools in terms of tool support if we had some special symbol, such as null or done, that results in instance release. So if you set that for the value, a target value, then it would actually release the instance. A simple graph of kind of the simplest version of the envelope. So start at the value 0 and ramp linearly to the value 5 over 6 units of time. Here's a simple multi-ramp. So we just add some arguments for additional target and duration. If we use a vector for a target, then we get something like this. And similarly, we use vectors for durations, then we get something like this, which should all be trackable through this data structure. So here's what my example looks like using, so the ADSR envelope example, much simplified now, using this M function. So we just basically build the envelope, assign it to a variable E in this case, and then use a function that I've called lookup here that we just pass in the data structure E, the envelope, and then so the envelope object, and the current time, and it would give us the value at that point in the envelope. On the release block, we just redefine the values stored in the envelope object, including an instance release at the end. So example 7, this is getting much more complicated, arpeggiator with instance input and amplitude envelope. So now we're using multiple kind of experimental hypothetical features, including the self-time map proposal, the envelope proposal. But here I'm also instancing by index and have multiple destinations in the map. But the idea is just to try to explore what it would look like to make something that was I guess similar to the functionality that we get through MIDI, where we have these objects, these note objects that include both pitch and envelope, pitch and amplitude information. But in this case, we would be playing the envelope in a periodic function. So here, whenever we have a new, this should be whenever there's a new or release event, we would reconcatenate and sort the source instance values and to make a vector for pitch. And then we have two different periodic blocks. One that's being called based on this pattern, so it's at a relatively low rate, and that's playing the arpeggio. Whenever that's called, it's basically allocating a new instance of the two output signals. One is assigned the next value in the pitch vector. We create an instanced copy of, or an instance of the envelope for this particular instance. And we start the instance of the amplitude output at 0. And then we just increment the lookup value, the index for our pitches. Then we have another periodic block that's running at 10 milliseconds, every 10 milliseconds. So this is the kind of envelope generator, right? So using the lookup function, passing in the envelope, which is implicitly, we get the correct instance. In fact, we would calculate this for all the active instances of the output. And we pass in the current time, and we use it to drive the amplitude output of this map. And then we would evaluate whether that instance is still alive as part of that periodic block as well, so that it can, once it's done, it would just release, which would have to be part of our envelope definition actually in the first periodic block. Okay, so that was it for the discussion of this proposal about time maps. Love to have some feedback, some discussion. I'll try to copy some of this, at least the more important points, into text and put them in the discussion group as well. But looking forward to some hopefully lively discussion about this topic. Thanks a lot. Bye.